the focused questions for the grade 12 advanced end of year exams. We start with the term 1 materials. The first question is to write the unit of K for the 0, first, second, and third order. So for the rate law, I'm going to write first the rate law of each order. For if the reaction is a 0 order, the rate law would be the reactant A to the power of 0, saying that A will give a product, that's the reaction. If the reaction is of first order, the order of A is going to be 1. If the reaction is of second order, the order of A is going to be 2. And if the reaction is third order, A would be to the power of 3. Now the unit of K will change depending on the order. I would like to mention here in the first order, since it is to the power of 0, it means I can write this rate law as R equal K. And therefore, the unit of K would be the same as the unit of the rate itself. So the unit of K will be molar per second, or simply write M as minus 1. Note that M is mole per liter. So to make it easy, use the symbol capital M. If the reaction is of first order, the unit of K would be simply S minus 1. So it's per S per second, or S minus 1. So there is no more M molar in it. Now you follow this rule. You look at the order and you put one number less. So it's second order, that it's going to be M minus 1, S minus 1. If this number is a 3, then I'm going to say M minus 2, S minus 1. If I have a fourth order, it's going to be M minus 3, S minus 1, and so on. So the unit of K depends on the concentration and the order of the reactant. This question asks to write the rate law of a given equation, of a given reaction that has 3 reactants. So the rate law is going to be A to a certain power, to a certain order, B to another order, and C to another order. Now let's see the given. The rate says, the rate is given to us. So it says A to the power of 2. It means that it is second order in A. And on B, if there is no number, it means that's first order in B. Now, since in the formula of the rate law there is no C, and C is a reactant, it means that it is a 0 order in C. Again, if it's a 0 order, you can simply not write the C in the formula. In this question here, the next question, they are asking you to write the rate law of given data using the method of initial rate. So here the reaction is of 2 reactants, A and B. So the rate law is going to be A to the power of N, which we will determine right now, and B to the order or to the power of M. So how do we do this? If I want to calculate N, the order of A, I will select the experiments in which B is not changing so that I can study the effect of A changes on the rate. So I'm going to choose experiment 1 and 2. And always use the larger number divided by the smaller number raised to the power of A. So it is 0.819 over 0.273 to the power of N equal. That's the rate when we change the concentration of A. It's 25.47 over 2.83. So that is 3 to the power of N equal 9. Therefore, it is second order in A. Now, if I want to calculate the order with respect to B, therefore, I am going to choose the experiments in which the concentration of A is constant, not changing. So that means experiment 1 and 2, and I'm going to study the effect of changes in B on the rate law. Now, this doesn't need calculations because you can see that when B concentration changed from 0.7 to 1.5, the rate did not change. Therefore, it is 0 order in B. Or, if you prefer, you can divide the larger number over the smaller one raised to the order of B equals 2.83 over 2.83. That is 2 to the power of m equal 1. Therefore, m is 0. And when we write the formula, we're not going to include C in that formula. Now, finding the value of K, you can use any experiment here, any trial. So let's say if I took the second one, I'll just substitute in the formula of the rate law. So R is equal to 2.83, K, which we are going to calculate, multiplied by the concentration of A, raised to the second order, raised to 2, power of 2. And K would be 39.7. Now, since this is second order, it's going to be M minus 1, S minus 1. Moving on, this shows here another type of questions where instructions are written for you. A reaction was found to be second order in carbon monoxide. So when I'm writing the rate law, it is second order in CO. The rate of the reaction if the CO is doubled when everything else is kept the same. So what happens to the rate of the reaction if I double the concentration of CO? So you can simply use this method. They said here double. So you take 2 and you raise it to the power of 2 equal. So here, what would be the rate? 2 to the power of 2 equal 4. So the reaction rate will increase 4 times or by a factor of 4. Another example, if the rate law of the first order in A, so I have a reaction first order in A and second order in B, so I have a second order in B, then the rate law, that's it. So here's the answer. Consider the following reaction between L and Q. So I have again rate L, which I don't know yet the order, and Q, I don't know yet the order of Q, so I'm going to name them N and M. Then the question says, the group 1 instruction says, when the initial concentration of L was doubled, the rate quadruples. So when I double, the rate quadruples. So N is second order. So now I know that the order of L is second order. And when the initial concentration of, let's continue. When the concentration of Q doubles, the rate doubles. So when Q doubles, the rate doubles. Therefore, the order of Q is first order. Again, another group. When the initial concentration of L was doubled, the rate quadrupled, which means again that L is second order. When the initial concentration of Q was tripled, the rate was tripled. So whenever you do a change, you put that change raised to the power of the order. And here they said the rate tripled, so I'll write 3. So M is equal to 1. Now deduce the overall order. You add the orders of L and Q, so that is third order. And when they ask you to write the rate law, you simply put R equal K. Do not forget the rate constant. It is equal to the concentration of L raised to 2, order of L, and Q raised to 1, or just simply Q. Let's take another example. A student carried out a pair of experiments and to investigate the rate law of the reaction. Note that when I write the rate law, I'm not interested in including the products in the formula. It's only equal to the concentration of the reactants. So this is power N and this is power M. So let's see. When the initial concentration of NO- is increased from 0.2 to 0.4, from 0.2 to 0.4, that's the double. Or you can simply divide the larger number by the smaller number, that is equal to 2. So they said that the rate is doubled times 2. So I'm going to write here 2. 2 to the power of n equal to, therefore, first order with respect to NO2 minus. Now, again, let's see the second experiment. It says, when the initial concentration of NH4 plus is increased from 0.03 to 0.06, that's also, again, we're doubling the concentration of NH4 plus. Or if you're not good with numbers, you can divide the larger number by the smaller number raised to the power or to the order of NH4 plus. Then continuing the sentence, they said the rate doubled. So 2 to the power of m equal to, therefore, also it is first order with respect to NH4 plus. So now we know that this one is equal, it's 1 and 1. You can just simply put the brackets without adding 1, or you can simply put 1 and 1. Deduce the overall order, so you add 1 plus 1 equals second order. And write the rate law. Therefore, the rate law is NO2 minus multiplied by the concentration of NH4 plus. Now, moving on to the materials of term 3, where you have to name alkenes or draw them, naming and drawing, and naming alkynes or drawing alkynes. Now, which of the following is correctly named alkene? If I have an alkene, the naming should end with "ene", and that is ending with "ane", definitely not the answer. Now, this one has 2 numbers. When I have a double bond in the name, I should indicate where is this double bond located on the main chain. So having here 2 numbers means there's a branch, and the name of the branch also is missing. So that's definitely wrong. Now I'm left with B and D. So try to draw and see why one of them is wrong. When they say 3-butene, 1, 2, 3, so the double bond is here. And when they say 1-butene, the double bond is here, or if I started from this side. So when I want to name an alkene, I should start from the carbon that is closer to the double bond, meaning here option B is wrong because they started counting from the wrong side. Name the alkene. To name an alkene, we choose the longest main chain and we count how many carbons we have in it. 1, 2, 3, 4, 5, 6, 7, 8. 8 means an oct. Now I have a double bond over here. So I should count from the side that is closer to the double bond, which is from the left. 1, 2. When I reach the second carbon, the ene is on the second carbon. So the main chain is going to be octene on the second. Again, I have 2 branches. Each branch is of 1 carbon. So that would be a methyl on the 4th carbon, 5th, and then another methyl on the 6th carbon. So therefore, the name is going to be 4, 6. Since this is the same naming, so I'll put the numbers together and say dimethyl 2-octene. Next, you are given a branch chained. So there are branches. Okay. Alkene. So there is a double bond which is over here. Contains 1 double bond and 2 alkyl. YL means I have branches. So the longest continuous chain of carbon that includes the double bond is of 7 carbons. 1, 2, 3, 4, 5, 6, 7. And that would be, what's the name of 7? It's hept. Now, since this is an alkene, it should be ene. And where exactly this ene? It's on the 2nd carbon. So I can simply say heptene or 2-heptene. Substituent means branches. So I see 2 branches. Each one is made up of 1 carbon, and 1 means meth. Now, since this is a branch, I'll add the termination YL. You can see here YL for branches. Let's move on to a question where we have to draw or name. This one is an alkyne. So the main chain is this one. That's not a branch. A branch cannot be on the last carbon. So that's just a straight chain, but in drawing it, they preferred to put this group up. So that would be the same. So 1, 2, 3, 4, that's a but, 4 carbons. Now this is a triple bond, so the termination ine, because it's an alkyne. Now where is this ine? It's on the first carbon. Another example, you start reading the name from the last and you break it. So I have an ene, it means I have a double bond. There's a double bond somewhere. Where exactly? On carbon number 4, and the whole chain is made up of 8 carbons. So 1, 2, 3, 4, I'm gonna put the double bond here, 5, 6, 7, and 8. So the rest are single bonds. Always when you are drawing, you have to surround C by 4 lines, 4 bonds, 4 single or 1 double, 2 single. So this carbon has 1, 2, 3, 4, so no more bonds. And this one as well, 1, 2, 3, 4. This carbon, 1, 2, 3, 4, 1, 2, 3, 4, 1, 1, 2, 3, and 4. What else we have on this, in this branch, in this hydrocarbon? We have on the third carbon, which is this one over here, we have a group of 2 carbons. Eth means 2 carbons. So 1 and 2. You cannot disconnect these carbons like 1 here and 1 here. That's wrong. So you have to connect these carbons because they are consecutive to ethyl. And that's it. You're done. Do not forget to add the hydrogens. Okay. That's for the naming. Now let's move on. Choose from compounds X, Y, and Z the alkene and the alkyne. The alkene and the alkyne. So that's the alkyne and that's the alkene. How do I know? I just look to locate if there is, to see if there is a double or triple bond. That's an alkane, in case you are wondering. Again, naming or drawing. The first trick here is to choose the longest chain. So you pick a side and you keep until the last carbon you can reach. So that's the main chain with 1 branch. And I should start counting from this side because it's closer to the branch and closer to the double bond. So I have a branch of 4, a main chain of 4, that's a but with a double bond, so I'm going to write ene. Now, where is this ene? It's located on the second carbon, so I'm going to say 2 ene. And also on the second carbon, I have a branch made up of 1 carbon, which will be called methyl. So the name 2-methyl, 2-butene. Another example, oct means 8 carbon. Always when you're reading a name, start from the last. Ene means I have a double bond. Where exactly? On the first carbon. And on the second and the fourth carbon, I have 2 same branches. Each one is called methyl, 1 carbon. So let's first put 8 carbons. 3, 4, 5, 6, 7, 8. On the first one, there's a double bond. So the rest are single bonds. Okay. Let's put the other bonds to make sure that we don't miss the hydrogens. As I said, this carbon, 1, 2, 3, 4. We're done. Now this one here, 1, 2, 3, and 4. Now on the second and on the fourth. On the second, I have 1 carbon, 1 methyl. And on the fourth, I have another methyl group. And that's it. You're done. So don't forget to add the hydrogen atoms. Please do not write hydrogen like that. That's wrong. Capital letter. And the last question. Here's the main chain. This side is closer to the double bond, 1, 2, 3, and 4. And I have a branch made up of 2 carbons. 2 carbon branch is an eth. Since this is a branch, it would end with YL. Now your main chain is of 4 carbons. 4 carbons means a but, and there's a double bond, I will say ene. Now where is this double bond? It's on the first. So the name is gonna be butene 1. You always put the number before the name of the main chain. And on the second carbon, I have an ethyl. I have 2 carbons consecutive, that's an ethyl, located on the second carbon of the main chain. Thank you. Point 2. Define the acid ionization constant Ka, and you also have Kb in this topic. So Ka is the ionization constant. How to write the expression of Ka? So the equation is at equilibrium. And when you are going to write the formula of Ka, you always take whatever you have in the products divided by whatever you have in the reactant, the acid itself. You do not add the formula of H2O in the equation. So it's the concentration of the CO3 minus, the conjugate base of that acid, here's the acid, multiplied by H3O plus over the acid. We do not take water because it's in the liquid phase. Now, some students, they ask, can I write H3O plus multiplied by CO3 minus over HCO3 minus? Yes. Others will ask, can I write H plus instead? Also, this is correct. Now, what would be the definition of Ka? Ka will show you how weak the acid is. So the value of K will show the strength of the ionization or dissociation of the acid. Moving on, we can use the value of Ka in order to order given acids from to check which one is the weakest and which one is the strongest among the weak acids. So the value of Ka, again, as I mentioned, will indicate how weak an acid is. Now, which of the following is the strongest acid? So we need to look for the largest Ka given over here. That's a -10, that's super small. This is -5 and this is -2, so it is 0.11. That's the strongest, but all of these acids are weak acids. Another question, they might give you different values of Ka and they ask you to order them, to arrange them, decreasing or increasing order. So in this question, decreasing means from the strongest weak acid, from the strongest among weak acids, so the strongest weak acid to the weakest weak acid. I always say weak acid because as long as there's a Ka, the given acid is weak. If Ka is a large number, like above 1, we're talking about a strong acid. So which one is the strongest? The one with the larger number. It's -3, means 0.0024 compared to -5. So it is 0.123416. So that's the strongest. Hy, then Hx, then Hz. You just have to compare the numbers and be careful to this. Now moving on to Kb. So again, Kb will show you the degree of ionization or the strength of a given weak base. The strength of a weak base or the degree of ionization of a base in water. So if it's a weak base, it will barely ionize. And the value of Ka, the numerical value of Ka will show that. Now write the expression again for Kb. I will take whatever I have in the denominator divided by the given base. So Hs minus multiplied by hydroxide ion over S2. And that's it. Now, Moving on to the next topic that involves calculations. In your formula sheet that is given to you in the exam, you need to look at the formulas and understand how to use these formulas. So I am going to write these formulas right here. So you are given pH minus log H plus. You are given POH minus log OH minus the hydroxide ion concentration. pH plus POH equal 14. And the KW, which is the concentration of H plus multiplied by the concentration of OH minus, which is equal to 1 times 10 to the power negative 14. Now I'm gonna tell you how to use these formulas. So first, start reading the question. If the concentration of hydronium ion in a solution is, so the concentration of hydronium ion, of H plus, hydronium ion is H3O plus, which is the same as H plus. So if H plus is equal to this value, so I have the concentration of H plus, calculate the concentration of hydroxide ion. In the formula sheet, they give you the formula of H plus and OH minus. Now follow this technique. Whatever is given to you in the question, highlighted in the formulas that you have. So I have H plus here and there. Okay, now what do they want? They want to find OH minus, which I find it here and here. I cannot use the first formula, I cannot use the second formula, because I don't have, it's not related to pH. They're not asking pH and POH. So in this case, I need to use the KW, where it gives me the concentration, one given and one variable. So H plus multiplied by OH minus is equal to 1.1 times 10 to the power negative 14, and I'm going to substitute X, and solving for X, you will find the hydroxide ion concentration equal to 5 times 10 to the power negative 10. Do not forget the unit, same unit will be molarity. Now, if a solution, now again, let me just erase this. So, I have a solution with a pH of 1. So the pH is given, and they want the POH. They want this, and I have the pH. So I can use the formula. There is no need to use this one, because here in this new question, they want, so if you think that here, OH minus. So I don't have H plus, I don't have OH minus, I only have the pH, and I need to find the POH. So I'll take this formula because I can use it. So 1 plus POH equal 14, POH is 13. Again, what is the POH? If pH is 6, I'm gonna use the same formula. The pH is given, the POH, they are asking about it. So according to this formula, it is equal to 14, POH is 8. Moving on, relate the acidity and basicity of an aqueous solution to the hydronium and hydroxide ion concentration and pH. So here they want to know how the concentration of OH minus and how the concentration of hydronium ion, H3O plus, or I can simply say H plus, it's the same. So they want to know how these concentrations will affect the pH of a solution. So the pH is a scale from 0 to 14, where from 0 to 7 is the area for acid, 7 to 14 is the area, any number above 7 till 14 is base, and if it is just 7, neutral. Now, if I have a pH if I have a solution with a pH less than 7, it means H plus are the dominant ions. So they are more than the concentration of hydroxide ions. Now, if I have a solution with a pH larger than 7, then this solution is basic, and the dominating ion in this solution is the OH minus. So in base, OH minus will be dominating the H plus. So that's how I think about it. Now, if I have a pH that is equal to 7, at that point, these ions are equal. I can simplify it like that. If I have a pH scale from 0 to 14, as the pH scale increases, the concentration of OH minus increases and the concentration of H plus decreases. Now, if I have the same pH scale, 14 and 0, but the pH of a solution, if I'm comparing solutions, is decreasing, is getting less. At that point, OH minus is also decreasing, H plus is increasing, and pH, as I mentioned, decreasing. Here pH is increasing. Moving on with the questions. Use the following information to answer the questions. They want the most acidic, the most basic, the neutral, and the least basic. So before we start comparing, let us find the pH of all these solutions. So pH is given, pOH is given, so I can find the pH by doing this formula, equal 14. So the pH is equal to 10.9. So solution O has 10.9. Now, if you look at this one, the concentration of OH minus is equal to 1.0 times 10 to the power negative 7. When the concentrations of OH minus and H plus are equal, they are equal to this value as well. And that's the case of neutral solution. So here pH is 7. It doesn't need calculations. Now, I have here H plus. So I'm going to plug this into the calculator. So minus log of this value. The answer is going to be 1.7. So here's pH equal 1.7. This one pH is given. And the last one, I have OH minus. So if I look at my formulas, I have pOH equal minus log OH minus. And I have pH equal minus log H plus. And I have pH plus pOH equal 14. Which one is better to use? If I have OH minus, I'm gonna put it here and get the pOH, and then I will substitute the pOH over here in this equation to find the pH. So let's do it. In this one, I'm going to say minus log of 2 times 10 to the power negative 5. And that is equal to 4.7. And then I'm going to substitute here pH plus 4.7 equal 14. And the answer is 9.3. So the pH is 9.3. So here we go. We have all the pHs in these questions. let's start answering the questions. The most acidic is the one, I'm going to keep this one here. So the most acidic is the one that has a pH super close to 0. I'm going to draw this again. 0, 14, 7. As I go in this direction, it becomes more acidic. As I go in this direction, more basic. And if it is 7, it's going to be neutral. So the most acidic is the one with the lowest pH, and that is solution C, solution M, or option C. The most basic is the one having the highest pH, and that is this one, option E. The neutral is the one having pH 7, and that is option D. The least basic means most acidic. That's what it means, most acidic. And that is again option C. Now let's continue our calculations. Calculate the pH of a solution if the concentration of H plus is given. So pH minus log the given concentration. And pH is 4. If the concentration of H plus is given, what is the pOH? In these questions, use the formulas and highlight the given and what you need to find. That's the best way to avoid mistakes. H plus times OH minus, that's the KW. So H plus is given, they want pOH. Okay, so it's gonna be a two-step equation. First, I'm gonna use equation 1. I'm gonna use equation 1 to find the pH. Then I'm gonna plug the pH into equation 3 to find the pOH. So it is minus log 1 times 10 to the power negative 5, that is equal to 5. And then using equation 3, 5 plus pOH equal 14, pOH equal 9. Write the relationship between pH and pOH. It is equation 3. Now, what is the relationship between H plus and OH minus concentrations? That's the constant ionization of water, W. That's why we call it KW. And it is equal to the concentration of H plus multiplied by the concentration of OH minus, and that is equal to a constant that is specifically at 25 degrees Celsius. Moving on with the questions. The diagram below shows the pH of 3 different solutions, W, X, and Z. Answer the questions A and B. So I have a pH given here, 11, 5, and 8. That's acidic. That's above 7 basic, and that's above 7 basic. So classify them as acid, base, or neutral. I don't have any neutral solution here. W is basic, X is acidic, and Z is basic because it's above 7. Now, moving on to topic 6.4, the titration. Define titration and titrant. In this, I'm just going to check if I have a photo. No, I'm going to draw a titration here for you. In the titration, you usually have a burette. You're holding it above a conical flask. Now, this burette usually is filled with what we call the titrant, and that is the solution of known concentration. We use it to titrate We use it in order to do titration for a solution that is in the conical flask, but the solution in the conical flask, we don't know its concentration. So it is called analyte. And it's the solution with unknown concentration. Now, what's the difference between titration and titrant? Titration is the technique, it's the experiment itself, the process. While titrant is the solution of known concentration that is filled in the burette. So, titration, so as I mentioned, I'm not gonna write it just because of the time. Titration is the technique, it's an experimental technique that we use a solution of known concentration and we add it drop-wise to a solution of unknown concentration for the purpose of determining the concentration of that unknown. So it's a technique, we use it to find the concentration of an unknown acid or base. Titrant is the solution that is added in the burette and it has a known concentration. Explain the difference between equivalence point and end point. Like the word is saying, end means stop. Equivalence point is something equal. So end point of titration is at the point at which the titration should stop. And that is when the indicator changes color. So the end point is the volume at which the color of the indicator, or at which the indicator changes color. So at which the indicator switches or changes color. And it has to be slightly, a faint change color. Okay? And it's usually obtained slightly after the equivalence point. Now, equivalence point, what is the equal thing? Equivalence point is the point at which the moles of the acid are equal to the moles of hydroxide ions. So at that point, the acid and the base neutralize each other. They reached a point where they are equal. So we call it equivalence point. Equivalence point, it comes right before the end point. We cannot see it with our eye. So we need an indicator that it switches color from an acid to base and vice versa, medium. So therefore, we know that we passed the equivalence point. Now, complete the table. Titration type of salt, equivalence point, the pH at equivalence point, the indicator, and the color change. Okay, so if I have a salt formed, now looking at this salt, this is a neutral salt because it's coming from a base that's basically an AOH, because it's a base, and it's coming from an acid. The acid, you add the H at the beginning, HCl. Now, if you look at these formulas, sodium hydroxide and HCl, both of them are strong. So it is the titration of a strong acid, and I'm titrating it with a strong base. So if I have here in the burette, I have the base, and in the conical flask, I have the acid. The equivalence point when both acid and base are strong will be 7. And the best indicator used for a strong titration is phenol phthalate. Now the color change, since in the conical flask I have an acid, the phenol phthalate is colorless with acid but is pink with bases. So the color is going to switch from being colorless to pink. Now, Let's look at this other example. Here I have CH3COO and I have Na. From Na, I know that this is coming from the base, NaOH. And this one is coming from the acid, that is CH3COOH. That's acetic acid, carboxylic acid. So that's a weak acid, and that's a strong base. That's a strong base. Therefore, when we do this titration, it's a titration of a weak acid with a strong base. So here in the burette, I have a base, and in the conical flask, I have a weak acid. So the equivalence point will follow the strong base, and it's going to be above 7. And the best indicator again is phenol phthalate, which is going to change from colorless to pink. Next, draw and label the titration curve of a strong acid with a strong base, and the titration curve of weak acid with a strong base. So first, let me just put the y and x-axis. So in here, I'm gonna do the titration of strong acid with strong base. Always when you do a graph, you make sure to label the y-axis and the x-axis. So the y-axis is always labeled as pH, and the x-axis is always the volume of the titrant. And in this case, you are titrating with a strong base, so it's going to be the volume of the base, this one, in milliliter. Now, since this is strong, our curve is going to start from being acidic to being basic. So we start, just mark the important points at the curve. The equivalence point of a strong will be obtained at pH 7. So here you have to label 7 on the pH scale, you have to label 0, and you have to label 14 at the end. And when you start with the curve, you start near the 0 with an almost straight line that is increasing, slightly increasing, and then suddenly, that's the best I can do, it jumps suddenly. And half of this, I'm gonna try again. So, yep. So the middle of this curve, you have to indicate it to show that this is the volume at equivalence point, and this is the pH at equivalence point, and it's equal to 7. Now, if I have a titration, if I want to draw a titration curve of a weak acid with a strong base, that's what I'm gonna do. Weak acid with a strong base. So here's the graph, y-axis and x-axis. As I mentioned, it has to be, you have to label it, and that's the volume of the titrant. It's always, I'm titrating with the base, so it's the volume of the base. Now, since the acid that we are starting with is weak, therefore the equivalence point is obtained above 7. It's gonna follow the base above 7. So make sure you put 7 on your graph, and the middle of the curve, you'll do it above 7. Now, here, this is the graph starts at 0. You start your curve far from 0. And when you start your curve, you start with a slight jump. You see here, there's no slight increase. Here, there's a slight jump that I'm showing at my curve. So there's a slight jump, and it keeps on, oops, overreacted. It keeps on increasing. So half of this curve is gonna be above 7. So here I am showing on my graph that it is above 7. So these are important points that we look at when we are looking at the titration curve. Now let's move on to the assigning oxidation numbers of compounds and ions given. Again, I would like to mention that on my YouTube channel there's a playlist named I think electrochemistry. If you look at it, you will find a video recording explaining how to find the oxidation number of any given substance. Now, briefly, I'm just going to put some points. In free elements, oxidation number is always 0. If I have an ion, the oxidation number will be the charge of that ion. If I have a monoatomic ion like X plus, for example, so X plus, the charge, the oxidation number will be plus. If I have an ionic compound, I can use the periodic table. Any element in group 1 will have oxidation number of +1, group 2 +2, group 13 +3. In the ionic compound itself, the anion, like the negative part of that compound, if it is group 15, it's going to be -3, 16 -2, 17 -1. Now, there are some other rules that we need to memorize. In polyatomic ions, since we have non-metals, we cannot rely on the periodic table if I don't have an ionic compound. In this case, I have to remember that oxygen is always -2 in compounds, except in peroxides it's -1. F is always -1 without any exceptions. Hydrogen is always +1, with exception in metal hydrides, hydrogen is +1. Now, follow this technique in solving and finding the oxidation number. Na belongs to group 1, so it's a +1. Cl, that's not an ionic, this is a polyatomic ion, so I need to put the oxidation number of Cl as X. I don't know it. Now, O oxidation number is -2, 1O, and you have 4 of it, so you're gonna say 4 times -2 equal to how much? If we look at this formula, there's no charge over here, therefore it's equal to 0. Solving for X, we will find the oxidation number of Cl to be +7. Again, AlPO4, Al belongs to group 13, that's a metal, so +3. P, I don't know it. And oxygen, as I mentioned, it is -2, but I have 4 oxygen in the formula, equal to 0. So solving for X, we'll find the oxidation number of phosphorus +5. N in HNO2. H oxidation number always +1. That's not an exception of a metal hydride. So H is +1. N, we don't know it yet because there is no rule that can tell us what's the oxidation number of N. It keeps on changing. And again, oxygen, as I mentioned, is always -2. But you have 2 oxygens, so multiplied by 2 equal to 0. Solving for X, we'll find X to be +3. Now, look at these 3 examples. This one and this one and this one. In here, the given polyatomic ion is charged, so I'm not gonna say like these previous examples equal to 0. So, N, I don't know it. H, I know it. It's always +1, and I have 4 hydrogens. Now, instead of saying equal to 0, I'm gonna say equal to the charge that is present here. This one is NH4 plus, so that's the charge. If the 4 is written up like that, the charge will be 4 plus. So please be careful to this common mistake. So that's a +1. Solving for X, we will find N to be -3. So here, you see, N can change. I cannot memorize it. Now, This one, AS is unknown. Again, 4 times negative 2 equal negative 3. Solving for x, it's going to be positive 5. So I'm going to move on. X plus 4 times oxygen atom. Each one is negative 2, and that is equal to negative 2, equal to the charge outside. Solving for x will give me positive 6, the oxidation number of chromium. Now again, these two examples are neutral, so I'm going to be back again to write equal to 0. So N is unknown, and H, I have 3 hydrogens, each one is positive 1, so N is negative 3. Now, be careful to this example. You have N2, so the unknown is multiplied by 2. X represents the oxidation number of N. So it is multiplied by 2 plus 4 hydrogens times 1 equal to 0. So solving for X, we will find the oxidation number of N, negative 2. Last one, again, I'm going to write it in a better way. That's a negative 1. If you're going to write negative 4, the 4 must be placed up, which is not the case. So, oxidation number of manganese plus 4 times the oxidation number of oxygen, which is negative 2 each one, equal to negative 1. Solving for X, we get it plus 7, the oxidation number. I'm going to move on. Now, given the following substances, in which of the substances does the oxygen have the given oxidation states? Okay. Now, let's go back again and explain the oxidation number of oxygen. Oxygen in free elements like ozone or O2, it is 0. So 0, it has to be for a free element. So in this case, it's O3. If no exceptions, oxygen in compounds, in any compound, H2O, CO2, HClO4, any compound, oxygen is going to be negative 2, and that's what we did in this previous question. So here, let's see. It is CuO, but maybe if you did not recognize it, I'll just explain to you how to guess it. I'm going to write now CuO, and after explaining these two, you will automatically know that the negative 2 was for CuO. Now, when is the oxidation number of O negative 1? That's an exception that you find only in peroxides. And what are the peroxides? Peroxides are compounds like H2O2, Li2O2, Na2O2, yani oxygen with group 1, but they're taking both 2. There's a peroxide ion, K2O2, all of these are peroxides. So this one goes for the exception of peroxides. Now, think about it logically. Let's say you forgot. Think about it logically. Na oxidation number is always positive 1. So I have 2 Na in the formula, so it's going to be positive 1 twice. Oxygen here cannot be negative 2 twice because there won't be a balance in the charges. So definitely here, I'll know that oxygen is negative 1 each to balance the charges. Now, we still have plus 2. You've never seen O to be plus 2, and that's definitely in an exception. Now, let's look at the choices given to us. F in compounds is always negative 1 without any single exception. Therefore, the exception here is the oxygen. So let's solve for it. I'm going to put O as X plus 2 multiplied by negative 1 equals 0. X is positive 2. Don't worry about this example. The exception is this one. There is no other option where O is positive 2. So if O is positive 2, It's either this given in the question or there is no option of positive 2. Now, moving on, distinguishing between oxidation and reduction. Again, you can check my channel and watch the video about oxidation and reduction. Oxidation is the loss of electrons, or in other words, it's the increase in the oxidation number. And you're going to understand why I said this once I start solving this question. Reduction is the gain of electron. Is when a substance gain electron, we say that the substance got reduced. Or in other words, it's a decrease. I'm going to use a better word that's similar to reduction. It's a reduce in the, or a reduction, something that gets less, that decreases in the oxidation number. Now, let's look at the species given to you. They want to know which species are oxidized, which species are reduced. First of all, you have to know that when you answer these questions, you cannot choose any answer from the product side. It's those reactant, which one is oxidized, which one is reduced. So that's it. Now, how to know the species oxidized and the species reduced? Since you know the oxidation number, check which substance is having an increase in the oxidation number or which substance is have a reduction or decrease in its oxidation number. Once you know this, then you know which one is reduced and which one is oxidized. So, Cl2 being a free element, it's 0. And over here, it's negative Cl minus. So the oxidation number of an ion is the charge itself. So there's a reduction from number 0 to -1. So Cl2 is the substance reduced, therefore the other one is the substance oxidized. Now if you wrote it with 2, it's fine, it's okay. Next, a free element, an element coming alone, oxidation number will be 0. However, when it changed, the oxidation number turned to 0, so to +3. So the oxidation number increased. So increase in the oxidation number means that the species oxidized, which is Ce. Again, if you wrote 2Ce, it's fine. If this is oxidized, then this one reduced. And look at it, from +2 to 0. It is a reduction. Now, when you write the answer, what I wrote right now is wrong. Because if I write it like that, it means I'm assuming it's Cu, which is wrong. You have to be careful to put the +2 on it. The 2 plus or +2, it doesn't matter here. Okay. Now, oxidized, again, increase in the oxidation number is an oxidation. A reduction, it's a reduce, it's a reduction. That's 0. I'll go for the simple one. O in free element is 0, and O in compounds is -2. So the oxidation number dropped from 0 to -2. So O2 is the species reduced, therefore Zn is the species oxidized. I don't have to solve it all. I will choose the simple ones. I know that H is +1, it's written on it, and I know that H2 in free element is 0. So from +1, it dropped to 0. H plus reduced. Na oxidized. Again, H in free element is 0. H in compound is +1. It's the same thing, it dropped. So, you can say here, wait, sorry, I wrote in the wrong place. HCl reduced and Zn oxidized. Or you can say H plus in HCl reduced and Zn oxidized. But it's fine. This answer is enough. Now predict the oxidizing agent and the reducing agent in a redox reaction. Before I move on, any species oxidized is also called reducing agent. Any species reduced is called the oxidizing agent. So, here in this question, next to this one, write reduction so that you don't get confused. And next to this one, write oxidation. And start comparing the oxidation numbers. That is a free element 0 and it increased to 2. So Fe undergoes an oxidation and that is a reducing agent. Of course, as I mentioned, you will never pick up an answer from the product side. So the reduction is silver ion or just Ag+. Now, I2 and Mg in a free element is 0. Mg belongs to group 2, that's a positive 2. So magnesium got oxidized, so it's called a reducing agent. I2 is an oxidizing agent. Similarly here, H is 0, free element, turned to positive 1 in compound. H got oxidized, meaning it's a reducing agent, and 2 is an oxidizing agent. For more practice, check my video tutorial. Definitions. Define half reaction. It's a half thing. Oxidation half, reduction half. Let me start with oxidation half reaction. Oxidation half reaction is when a substance increases in the oxidation number and lose electrons. So let's say I have X, and X increases in the oxidation number. It was 0 and it increased to +1 by losing electrons. Because how the oxidation number increases when we remove those electrons out. So it shows the species. So the definition of oxidation half reaction, it's a half equation. It's a half reaction showing an increase in the oxidation number, or you can say showing how a species is losing electrons. Reduction, it's completely the opposite way. If I have X plus turning into X, the oxidation number is getting reduced. Why? Because X plus was added, we added to it an electron, gained electron. So the oxidation number dropped. So a reduction half reaction is a half reaction in which a species gain electron and decreases in the oxidation number. Now together, oxidation and reduction, they happen together. So when I have an overall equation, I call it a redox. Overall, reduction, oxidation. Now what's a half reaction? A half reaction is either oxidation, half reaction, or reduction, half reaction. This whole thing is a half reaction. Now, predict the oxidation half reaction and predict the reduction half reaction. It's all related to the oxidation number. The oxidation number was 2, dropped to 0. That's a reduction. So you take this substance, change to this, and you write it. Now, note that a half reaction has to have electrons. So if it is a reduction, it's a gain of electrons. So you're going to add the electrons on this side. However, how much electrons you have here depend on the charge of the the species getting reduced. There's a 2 plus, and here it's a 0. So to balance the charges on both sides, 2 plus and 0, we add 2 electrons over here. That's the reduction half equation. And the oxidation half equation is the other one, where Cr loses electrons and increase in the oxidation state. So this side is 0 charge, this side is positive 3 charge. So that's the higher side. I'm gonna add 3 electrons to make it equal and balanced on both sides. And next, balancing. This could be tricky. So I advise you to check my channel and watch the video of balancing oxidation reduction in acidic medium. So when you have an equation like this, we split it into two halves. I'm gonna do the first, I'm gonna larger my screen and try to do the balancing over here. I have H2C2O4 changing to CO2. I'm gonna start with the steps. First, you balance the atoms that are not H and not O, which is C. I have here 2 carbon and I have here 1 carbon. To balance the atoms, you add coefficients. You balance them by adding coefficients. So 2 carbon versus 1 carbon, I'm going to add the number 2 over here. So I balanced the carbon. Now, you balance O by adding H2O. You cannot change the steps. You have to follow them in the correct order. When there's a coefficient, don't forget to multiply with it. On this side, I have 4 oxygens. And on this side, I also have 4 oxygens. So oxygen is balanced. So there's no need to add H2O. We're done. Now, after balancing the O, you move to balancing the H by adding H+. So let's count. I have 2 hydrogens here, and on this side, I don't have any hydrogen. So in order to balance the H, you add H+ on the side that is needing hydrogens. So you add H+ over here. Now you're done with balancing atoms O and H. Now the last part is to balance the charge. In order to balance the charge, you need to count the charge on each side. There is no charge over here, so the overall, it is 0. And here, here it's 2H+. So don't forget to multiply 2H+ because here I have H2. So don't forget to multiply the charge by the coefficient. Now, this is the side with the higher charge. So you have to add electrons to drop it to 0 to make the 2 sides equal. So I'm gonna add 2 electrons on this side. And I'm done with the oxidation half of this equation. Now let's move on to the reduction. You have MnO4 minus Mn2 plus. So first balance the atom of Mn. 1, 1. Already balanced. Move on. Now balance the atom O by adding H2O on the side that requires oxygen. Over here I have 4. Over here I don't have any single oxygen. So I'm gonna add 4 H2O to get 4 oxygens. Now, after balancing the O, we start thinking about balancing the H by adding H+ on the side that requires hydrogen. Don't forget to multiply by the coefficient. I have 4 times 2, that is 8. So I'm missing over here 8 hydrogens, so it's gonna be 8H+. Don't forget the plus. Now, we're done with the atoms. We still have to balance the charges. 1 minus here versus 8 pluses. Again, don't forget to multiply by the coefficient. 1 minus and 8 pluses, that's a 7 plus. Here I have a 2 plus and a 0, it's neutral. So I have 2 plus. So it's a 7 versus 2 plus. So that's the side of higher charge. So you're gonna add electrons to this side to drop it to 2 to make them equal on both sides. So that means I need to add 5 electrons to make them equal. Now, you're in the last step. After doing the oxidation and the reduction, you look at the electrons lost and gained, and you multiply by the greatest common factor, or here I multiply by 5 because here there's a 5, and here I multiply this equation by 2 because here there's a 2. And I start copying it again. So 5 H2C2O4 plus 10 electrons here plus 2 MnO4 minus plus 16 H plus. Now I reached the arrow. 5 times 2, 10 CO2. 5 times 2, 10 H plus. 5 times 2, 10 electrons. 2 times Mn. And 2 times 4, that's an 8 H2O. Now when I look at the equation, I'll find electrons on both sides. I can cancel them. So I'm gonna erase the electrons here. They cancel out. Okay, so they cancel out. Also, I have 16 H plus and here 10 H plus. So 6 only will remain at this side. That's it. So I'm gonna, just for the space, I'm gonna put the 8H2 over here. And you're done. So in balancing this one, here should be a 5. Here should be a 2. Here I should also have 6 H pluses and 10 and 2 and 8 H2O. Okay. Again, if you find this topic hard, check my channel for the video tutorial of balancing. Now again, let's take this other example. ClO3 minus giving Cl negative. So first, balance the atoms. 1 Cl, 1 Cl, balanced. Second, balance the O by adding H2O on the side that is missing the O or has less O. So clearly, I need 3 O over here, so I'll add 3 H2O. Then, balance the hydrogens by adding H plus on the side missing hydrogen. Here you have 3 times 2. Don't forget to multiply by the coefficients. So you're missing here 6 H pluses, not H pluses. Now count the charges. Don't forget the coefficient. 6 pluses coming from the H's and 1 minus coming from this ClO3 minus. So the overall charge on this side is 5 plus. And the overall charge on this side is only the one coming from the Cl minus 1. So plus 5 plus versus minus 1, that's the higher side. How can I drop the 5 plus to minus 1? If I added 5 electrons, this is going to be 0, this is going to be minus 1. So it won't reach minus 1. I need to add 6 electrons. So therefore, we add 6 electrons on this side. And we're done with the first reduction. Now second one, SO2 and SO4 with a negative 2 charge. Count the S, 1, 1, balanced. Count the O, 4 and 2. I have 2 oxygens missing, so I'm going to add 2 H2O molecules. And this means that now I have 2 times 2, 4 hydrogens on this side, so I'm gonna add 4 H plus on this side. Now it's time to count the charges. No charges on this side, so that is 0. And here I have 2 minus, and I have 4 pluses. That's a total of 2 plus. Now how do I drop the 2 plus to 0? by adding 2 electrons on this side, and you're done. Now, the overall equation. This one there's 2, and this one there's 6. What's the greatest common factor? I'm gonna multiply this by 3 because 3 times 2 makes it 6, and here I have 6. And I'm gonna add both of them. So 6 electrons, ClO3 minus, 6H plus, then 3 times 2, 6H2O, and 3SO2, giving Cl minus and 3H2O and 3 times SO4 2 minus and 3 times 4, that is 12H plus, and 3 times 2, 6 electrons. 6 electrons cancels out. Now 6H plus, and there's 12, 6 will remain. 3H2O and 6H2O, so 3 will remain. So the final one is, this one I can erase, this one I can erase, and instead of the 3 I can put, the 6 I can put 3. This one cancels out. And instead of this one, I can put 6 H pluses. And that's it, the balancing. Here's another example for the MnO4 minus giving Mn2 plus. I already did it over here, so I'm gonna write it again, and I will explain the oxidation of the other one. So that is a reduction, MnO4 minus, and 8 H pluses giving, plus 5 electrons, giving Mn2 plus and 4 H2O. Now, an important thing, since in this question they gave you the physical states, make sure that you don't miss them out. Water is always liquid. Now the other oxidation is Fe, increasing oxidation state to 3 plus. Now this is solid, this is aqueous. That's a 0, that's a plus a 3. And this is the side with higher higher charge, so I'm gonna add 3 electrons. Now the overall equation is gonna be, this one is 5, so I'm gonna multiply this half equation by 5. And this one is 3 electrons lost, so I'm gonna multiply this by 3. And now I'll write it 3MnO4 minus AQ plus 24 H plus plus 15 electrons, which will cancel out later on, 5 Fe solid. Now 3 Mn2 plus 12 H2O and 5 Fe3 plus and 15 electrons. So look at it, 15 electrons, you can erase, they cancel out. Now I have here, okay, that's it, there's nothing else to cancel out. Now the next part is the galvanic cell. The galvanic cell. Galvanic cell, also known as voltaic cell, and it's a cell that converts chemical energy to electrical energy. So study carefully the parts of a galvanic cell. An important factor is that the anode in the galvanic cell is the negative terminal and the cathode is the positive terminal. Always at the cathode there's a reduction, and at the anode there's an oxidation. For more details about the galvanic cell, you can watch my YouTube video about galvanic cells in details. So, an important thing is to know from where the electrons are flowing, the ions in the salt bridge, from where they are flowing, to which side they are. So make sure you are familiar with this diagram. Now let's start with the first question. A galvanic cell operates spontaneously. When they tell me spontaneously, it means that's voltaic cell. That's a voltaic cell. Consists of one half cell that contains silver solid, silver Ag. So I have one half cell, silver electrode immersed in a silver solution, and one other half cell containing copper electrode immersed in a copper solution. It's always like that. What species are produced at the electrodes under standard conditions? Now, let's focus at the given values, the standard reduction potential given to you over here. You look at the values of the standard reduction potential. The one that has less voltage is the one that is going to be the anode, operate at the anode. And the one that has a higher voltage, it's the stronger oxidizing agent. So Ag plus is a stronger oxidizing agent, and it's going to operate at the cathode. Therefore, here, I know that this metal is the cathode, and this is the anode. Again, you can simply compare the numbers. The larger number would be for the cathode, the smaller number would be for the anode. So, saying that means at the cathode, I'm just gonna erase this, put it a bit far, and I'll give you a simple way to memorize it. So Cu/Cu2 plus. So we said that Cu is the anode, and we said that the silver is the cathode. At the anode, it's always like that. It's a more reactive, giving a solution, and at the cathode, it's an oxidizing agent giving more metal. It's like this. Memorize it in this order. So Ag is formed at the cathode. True. Cu2 plus is formed at the anode. Again, let's take another example. A voltaic cell operates spontaneously with the given below voltages. Before you read the question, look at the voltages. Which one is the larger number? That is the larger number. Be careful, that's in the negative. So this is the larger number. So definitely this is going to operate at the cathode, and this is going to be the anode. That's the cathode electrode, that's the anode electrode. So when we say electrode, you are not allowed to choose from the solution. These are cathode solution and anode solution. But when they tell me which one is the anode and which one is the cathode, I choose the solid metal. So anode is it's the chromium, Cr, and cathode is the zinc. Now the overall equation. Now here you go. This is simple. As I mentioned previously, at the anode, it's the metal giving the ion. You see, when I wrote it like that, it's the metal giving the ion. At the cathode, it's the ion giving the metal. So simply, the cathode, you copy the equation as it is. You copy this one as it is. Zn2 plus, plus 2 electrons giving Zn. And this one, you flip it, the anode. It is Cr giving Cr2 plus. Cr giving Cr2 plus and 2 electrons. Now, 2 electrons lost, 2 electrons gained. I can simply write the overall equation, I'm gonna write it over here. These two together, Cr solid and a zinc solution, zinc solid and the Cr2 solution. Moving on. So that's the overall equation. Now another question. A voltaic cell operates spontaneously with Mg as anode in Mg2 solution. So as I told you, in the anode, it's the metal giving the ion, and Cu as a cathode, so that's the cathode. I have a Cu solution, so it's the solution, it's a reduction. So they want the oxidation and the reduction have reactions occurring at the anode and at the cathode. So at the anode, it's the Mg solid giving the Mg2 plus and 2 electrons. And at the cathode, it's the solution giving the metal. Of course, we add electrons here since this is a reduction. This is an oxidation. Now moving on, almost there. Describe the standard hydrogen electrodes while identifying the importance of its electrode potential value and writing half-cell reactions of the two possible reactions that could occur at the hydrogen electrode. So definition. SHE is the standard hydrogen electrode, and it's a reference electrode. It's a standard, it's a reference electrode that we use it in order to get the potentials of other electrodes. Like for example here, how do we know that zinc is negative 0.76 or chromium is 0.91 or silver is this much or copper is this much? It's because all of these half cells electrodes were coupled with hydrogen electrode that has a zero potential. So whatever voltage we obtain on the voltmeter, it would be the electrode of the other cell coupled with hydrogen. So the standard hydrogen electrode is a reference electrode used to measure electrode potentials. Now we need to describe it, like look at the figure and say what you are seeing. So in this electrode, it consists of a hydrogen gas pumped in it, a hydrogen gas at a 1 atmospheric pressure, immersed. This tube thing is immersed in a solution that is acidic. So immersed, I have a solution, an acidic solution, or if you didn't know that this is acidic, you can just say an H plus solution having a 1 molar concentration, 1 molar concentration, and there is an electrode, which is a long rod electrode of platinum. So platinum electrode immersed in the acidic solution. Now why platinum specifically? Because platinum doesn't react with the H plus and with the hydrogen gas. So we need an inert electrode, an electrode that doesn't interfere with the reaction. It is just there to allow the transfer of electrons. Okay, so now this hydrogen electrode can operate as oxidation, or it can be at the anode and it can be at the cathode, depending on what is the other half cell with it. So whether it is Oxidation, it's going to be like that. Hydrogen turning into H plus. Now 2 hydrogens, so I'm going to put 2 and 2 electrons. That's at the anode. And at the cathode, if it was working at the cathode, it will undergo a reduction. It's just flip it to H plus, giving plus 2 electrons, giving H2. Now, an important thing that I didn't yet mention, that the voltage of the standard hydrogen electrode is 0 volt. And what's the importance? So it's a universal reference for other electrodes. It's a reference used to find the voltage of other electrodes. Now, calculate. Now let's move on to another question. Using calculating the E cell. So calculate the electrochemical cell standard potential of a voltaic with an overall reaction. So I have E cell as a formula. It's the E cathode. It's given to you in the exam, minus E anode. Now let's look at the given. Here in the given, I see that lead Pb changed to Pb2 plus. So again, I told you the metal that changes into a solution is the anode. Or that's a 0 oxidation number. And this one, it's a +2 oxidation number, so it got oxidized. And oxidation only happens at the anode. So this one is operating at the anode. Here I cannot rely on the numbers. What if they gave me a non-spontaneous one? So I have to follow the lead of the given equation. But anyway, they mentioned voltaic, but in some questions they might not mention voltaic. So you just have to be careful. And I told you that at the cathode, it's the non-charged going to the charged. So this is the cathode, or the one with a higher number. So E cathode minus E anode. And the value is E cell equal to 1.2 volt, which is a positive answer, larger than 0, therefore a spontaneous spontaneous cell. Next, comparing between electrolytic and voltaic cell. 3 important differences between electrolytic and voltaic cell. In electrolytic cell, we need a battery, so a power source is required. In the voltaic cell, we don't need a battery. Now, in the electrolytic cell, the anode is the positive electrode and the cathode is the negative electrode, whereas in the voltaic cell, anode is the negative, cathode is the positive. And the last difference between these two is that the voltaic cell changes chemical energy and generates an electric current into electrical energy, which makes it spontaneous. Whereas in the electrolytic cell, a chemical reaction cannot start unless we have a power source, a battery. So here, it's a non-spontaneous reaction that's not going to happen without the use of a battery. So it converts electrical energy into chemical energy. Moving on, almost done. We're there. So if you find this video long, just take a break, then continue. Write the oxidation reaction at the anode and the reduction reaction at the cathode for the electrolysis of molten PbBr2. First, when they give you molten ionic compound, if it's molten, you do not think about hydrogen gas and oxygen gas obtained at the cathode and at the anode. There is no such option. These options, you only think about them when we are talking about the electrolysis of aqueous, which is the next question over here. So in molten electrolysis, always it's very simple. You know, you look at the formula itself. Whatever is coming at the first, it's the substance, it's the metal obtained at the cathode. So at the cathode, I obtain lead. And whatever is written here is what I get at the anode. So now, let's first break down this question into a simpler way. When they say molten ionic compound, when an ionic compound is melted, it liberates its ions. So I'm going to obtain Pb2 plus in the liquid state because it's molten, and I'm going to obtain Br minus, even if there's a 2, ignore the 2. Br belongs to group 17, so it has a -1 charge and physical state liquid. Now at the cathode, I always have a reduction. It's the positive ion that's going to change into a metal. And lead, usually when it is deposited at the cathode, it is in liquid state. And there's an electron here equal to the charge. You can follow like that. Any positive ion given to me, it's going to be at the cathode. I'm going to add electron to it and form a metal. So if this is 2 electron, metal, 3 electron, metal, but this formula doesn't change. You erase the charge on it and you don't put any number next to X. Next, at the anode, this one, I have the bromide ion. Now the bromide ion will undergo an oxidation and it's going to change into Br2. I wrote Br2 not because there's a 2 here, but because I always tell my students there's a rule. Any negative ion in the electrolysis, it's going to turn into an atom with a subscript 2, a diatomic molecule. And now in order to balance it, you're going to add 2 electrons here, coefficient 2 here. And because I have 2 minuses, it's going to be 2 electrons. Now let's say if that ion in the question was -2, in this case you're going to add 4 electrons. If it's -3, you're going to add 6 electrons. But this formula doesn't change. If this part is not clear, watch my video tutorial about electrolysis. Now, last thing that I would like to mention, that the negative ions in the electrolysis, they're gonna come and gather around. They are attracted to the anode electrode. And the cathode electrode, which is the -1, it will attract the lead ions. So that's how it goes. Now, before the last question, it is saying write the oxidation reaction at the anode and the reduction at the cathode, electrolysis of aqueous. In the aqueous electrolysis, we don't only have to think about the ions of the compound. So I have Ki aqueous. Ki aqueous has K plus ion and has I minus ions. But since this is an aqueous solution, we also need to think about the ions of water, which are H plus and OH minus, which will be which will be also attracted to the anode and cathode electrodes of this electrolysis. So the H plus, so I'm gonna say here, it's the K plus versus H plus at the cathode, and it's the I minus versus the OH minus ions coming from water at the anode. Now, how we think about it, which product will be discharged at the cathode? The rule says, if the metal in the ionic compound belongs to group 1 or 2 or even 13, this metal will not be discharged. So do not expect K plus to give K. the hydrogen gas will be discharged, and the H plus of the water are going to give you the hydrogen gas. So at the cathode, I have 2H plus giving hydrogen and 2 electrons, hydrogen gas. That's how we do it. Now, for the electrolysis at the anode, we have to look at the anion of the ionic compound, the aqueous one. Now the rule says, it's very simple. If this second part of the ionic compound, if this anion is strictly Cl or Br or I, then I2 is going to be discharged, or Cl2 or Br2 in the case of Br. And we will not obtain oxygen gas. So here at the anode, it's I minus giving I2. Again, like I said, it's the negative ion that gives a formula like this with the 2 electrons. And this is aqueous and I2 is solid. If you find this topic difficult, watch my YouTube video, my video tutorial about electrolysis. Last question in this revision session. Suppose a powerful battery is connected between a pair of inert graphite electrodes that do not react, that do not affect the result of a reaction. They are dipped into a molten calcium bromide molten. So stop thinking about hydrogen and oxygen gas, because they will not be obtained if it is a molten electrolysis. This one will go to the cathode, will gather around the cathode, and I will obtain calcium metal will be deposited at the cathode, and the other one will be deposited at the anode. So I have a Br minus coming around the anode, attracted to the anode electrode, and they will undergo an oxidation, turning into Br2 plus 2 electrons. So identify the products at each and write their reactions. So the product at this one is the calcium metal, calcium is going to be liquid, and the product at the anode is going to be Br2 gas. Label the flow of electrons. Now, whether it is an electrolytic cell or a galvanic cell or a voltaic cell, the electrons, they always flow from anode to cathode. And that is from anode. Remember, in the electrolytic cell, anode is the positive electrode. So the electron, they flow from anode to cathode. And that's it. Thank you.